Hello everyone. In this lesson, let's work on sensitive data in our logger. Now, since we've configured our logs to work with TRPC mutations and queries, when we register, the password and the user's email will be logged. And that's not very good. Let's give it a try. Let's create a user, jcheo12341234. They registered. Let's look at our logs. Someone came and triggered a mutation where they specified their email and their password in plain text. This isn't good because we'll probably send the logs to some third-party services, and it's not right for passwords to go there. Also, all other developers who have access to the logs will be able to see these passwords. But that's completely wrong. It shouldn't be like this. We need to address this somehow. To sort this out, we need to somehow process this meta object and find all these sensitive fields. Let's say we create some function called retify_meta. What will this function look like? This function will look like the following. First, let's define the meta type because we will reuse it in many places now. Here's what the meta looks like, and meta it is. Here's the meta, and here's the meta. Now, let's look at the contents of the retify_meta function. Retify_meta is a function that takes meta and returns meta as well. How does it work under the hood? Suppose there is some function deep map that takes as input, in this case, an object, and recursively traverses all its keys, all the arrays in it, all the objects in these arrays, and so on. It does a full traversal, and for each such element, returns us information about the key and the current value. If we have a key called email, password, new password, old password, token, text description, then instead of the content of this field, we display this smiley with a monkey covering its eyes, I believe. But if it's not one of these keys, then we return the original value. And that's how we simply iterate over our object. Let's see how this will work. I've already created the function. Now let's analyze it. But let's first make sure it works as we intended. So let's say our JJ went to log in, enters his nickname and password. Looking at the logs, sign in, mutation. And here we see that the password is now encrypted, and the output, his token, is also encrypted, and it didn't leak into our log. In theory, deep map has been implemented many times, but all these deep maps work somewhat differently in their own way. I have my own implementation of this very deep map that works the way I like. It can also accept the path to this object element. So I can see which fields have passed before this, and therefore it might be convenient for you. You can, for example, fix this for some mutations, or, for example, only in a specific input. So nothing prevents you from doing something like this and checking the path here. Let's break down this deep map function. In the future, when we write tests together, we will also write tests for this deep map and make sure it works correctly. All right, let's dive into it. Here is the function itself. Yes, it's a fairly simple generic. We pass a meta as the first argument here, and this input is our generic param. Well, the type of our input will be a generic, and it's returned as well. This particular value is a previously defined type, which could be an innumerable variety of things. Okay? And here's the next thing. I'm going to cover this briefly, but I won't go too deep because it's just more JavaScript disassembling. Nothing stops you from putting this all into ChatGPT and asking how these things work. I remind you, this course is about integrating all sorts of technologies and creating your own comprehensive product. But these are specifics and should be covered in other courses and JavaScript programs. But at the top level, we'll still go through it. Here we need to avoid the problem where, during recursive traversal of an object, there might be inner objects that refer to themselves, and we might enter an infinite loop and everything will freeze and break. Therefore, we need to avoid this. To do so, we're creating a weak set called sin, and we'll pass it further into our recursion. This is necessary so that when we encounter something we've already seen, instead of going inside, we mark it as a circular dependency and move on past it. All right? Then we call the recursion itself. Here, as a second argument, we had replace fn. Here it is, this replace fn. That is, how we will replace data inside this object. We passed it, past the input itself, past our collection, with already seen items. And this is needed to later form a path to our object element. Initially, our path is kind of empty. We start from the root. When we go through our map, we just copy our object using lodash and the clone deep function. This is necessary so that we get a new original object here. If we suddenly change something in the returned value, it won't change in the original object. All right, and then we return it. Let's deal with the recursion function. This is the second function in this file. It is not exported from here. It's only for internal use. Here are all the parameters we just passed. And then what happens? We look. If we have an object function or symbol, it means there is a chance for circular dependencies. We check our collection of already seen items. Is there the thing that is in front of us? If it's already there, we mark this value as circular. And that's how we see it in our output. Then, if we haven't seen it yet, we simply add it to what we've already seen. And we move on. So this is a protection against circular references. Good. Then we start forming our result. Since we already have some input here, we actually recurse over absolutely the entire object. That is, even from the beginning, upon seeing the object itself, we also try to replace it with something. If it has some value in our replace function, then it will be replaced. Okay? So we call that very replace function passing the path, current key, and value that came here. All right. If nothing was returned in our resolve, then we return it, and no need to traverse. It's something like null, undefined, false, etc. So this is already final. But it could be that our result is, for example, an array. And then we will loop through the array and call the same recursion function. And there it will start all over again for each element of the array. If our result turned out to be some kind of object, but obviously not null, null is also an object, because if it were null, it would have returned here. All right? If it's an object, then we take all its keys and all its values, and, again, recursively go through them. Only this time we return it, not as an array, but as an object. All right? Here we go through the object, like this. Well, if it's not an object, not an array, and not something negative, then we return it as it is. This is roughly how it works. And for now, this is enough for me. Maybe something here isn't working correctly. If any of us encounter this issue, let's just fix this function. But for now, it seems to work well and performs its task. Here's our deep map. Again, the deep map function is in the category of you needed it, you wrote it once. If something breaks, you fix it, and then you copy it from project to project. Perhaps we might need it again somewhere, but it's easy and convenient to use. Good. Let's say we've set up protection against data leaks, and we can move on. Thank you all. See you soon.